Dzień dobry. Good morning. For today's video, we're going to be taking a look at a DHT11 humidity and temperature sensor. Now, based on other videos I've done on either temperature or humidity sensors, they're not real popular. If you're young and healthy, the importance of temperature and humidity isn't very important to you. If you've got asthma or other respiratory problems, humidity can be a real problem for you. If you've got a home or property or a business and you don't want damage to the property from having too high of humidity, again, knowing what that is very important. So there are very serious needs for monitoring and detecting and making readings of temperature and humidity. Now, this particular sensor is relatively inexpensive. I'll provide a link in the program and in the description so that you can find it, but I think it was around $5 on Amazon. And this one in particular, I might have actually picked up at a micro center. But nonetheless, it's a good sensor. It seems to be doing what I want. The accuracy compared to my other higher accuracy thermometers that I have around here seem to be spot on. So that part's really, really good. The unit itself is very small, very compact. This came with a mounted board so that it gives you the proper interface between your microcontroller and the device itself. It gives you the capacitors, resistors, etc. This unit is a 3-pin module. Some of them have 4 pins. But what we're really looking at are 3 pins, ground, voltage, and signal. That's really what you're going to need. Now, S might be marked as data instead of signal. We'll take a look at a data sheet here real quick. They are rather interesting data sheets. There's a lot of descriptive data, specifications, as mentioning the accuracy, plus or minus 5% relative humidity, which in the real world is pretty darn good. We're not looking at lab conditions. Temperature accuracy, plus or minus 2 degrees Celsius, which to me is a little bit on the weak side, but it works out really okay. It is good in that it is power supply can be between 3 and 5.5 volts, so that fits perfectly within the Pico situation with its 3.3 volt logic. Now here's the unusual part, and it's partially one of the reasons why I picked this one. The communication process is a serial interface, single wire, two-way, bidirectional, single wire. Not real common, but you do see it. And the data format for that communications is interesting, a little bit more complicated than UART, etc. So I went out searching for a library to make this easy for everybody. As mentioned in other videos, I have no desire to write libraries anymore for I2C or SPI interfaces, etc. They're fun, but just no desire to do it. But nonetheless, I did find one, and it was on a site on someone's Google Drive link. And so I did try to look backwards to see the origins of it, and I saw a reference for it in the MicroPython documentation for the DHT library. So I assume that's the beginnings of it. This might have been modified over time to accommodate the Pico, but nonetheless, I'm using it. It works perfectly good. I just wish I could give credit to the original author. But I really won't go into a lot of the interfacing detail because that can consume hours of conversation. So with that, let's turn our attention to the wiring. So we'll look at the Fritzing diagram. And as mentioned, my module has G, V, and S, S being our signal, and I've got that hooked up to this pin here. pin 28, GPIO, and then 3.3 volts, and then our ground signals all coming back. As you're looking at the real-world breadboard on my workbench, I had to use jumper wires, so my color coding doesn't match the fritzing diagram. We'll take a quick look at that again. Let me get a pointer here. There is signal, voltage, and then ground as the connections. I go through a jumper with a connector back to the Raspberry Pi Pico. Now let's dive right into the code. Here is the library. I'll be including that in the package that I'll be putting up on my website. But it's a typical library, very low-level stuff. This one's fairly well documented to a certain degree. But there is one note here, less than a second since last read, which is too soon according to the data sheet. You don't want to read this thing real frequently, more than a second in between, less than a second in between reads, which in reality, when you think about it, temperature doesn't change that fast, nor does relative humidity. So realistically, in practice, reading this thing every 15 minutes would be about the most frequent I would do if I were actually logging data. A couple other comments in here. And then this kind of a little bit explains the interface with the 40 bits of data that are being transmitted, and then how it's converted into bytes, and then a checksum is calculated, etc. For our end of it, from a programmer in our situation, all we're concerned with is we have the library and we can import it. And then from there, what commands to issue to read the data. Here's the source for the DHT11. And a note again about the sourcing for this library. We're going to import a couple of files. From machine, we're going to import pins so we can establish the data communications pin. We're going to import sleep to slow down our number of reads. And then from that DHT library right there, we're going to import capital DHT11 and this invalid checksum, which I haven't really figured out if it's even worthwhile doing anything with that or not, but it is accessed. We're going to set up a couple of variables that'll be useful in the program. We're going to have a temp offset C and a humidity offset. And what those are for is if you find that you're off calibration with your DHT11, say it's 1 degree off on Celsius, well, then you could put an offset amount in here and apply that to the readings automatically so that you are truly accurate with your readings. The next three variables here are variables that are used to either display the temperature on screen or do more with it, and those would be string type variables. That'll make a little more sense later on. We're going to create a pin, number 28, which is what I'm physically connected to, GPIO 28. It's an output, and we want to pull it down. We're going to create our sensor object from the DHT11 library and pass it the pin number that the communications will occur on. And we're going to wait a minimum of a second here. In fact, setting that up to 2 or 3 seconds is probably better. If this is too short of a time, you're going to get some very weird errors here about not reading enough pulses. What it is, this takes a second or so to power up, and then as we try to read it right away, it isn't fully powered, so we're only getting part of that data communication stream. In this case, I'm doing a while loop to read 20 samples. So that's what I've constructed here. Created a variable for reads, setting it to 20, and while reads is greater than 0, keep doing reads, reading the sensor. And then we're going to count down that variable once for every read. And we're going to sleep about 1/4 of a second between it, just so that I can kind of speed up this demonstration. I don't think you want to wait around for 8 hours or so of dead silent video while we're waiting 15 minutes between reads. So this is where you would put in a sleep duration for up to 15 minutes or something like that. I did put in error handling. We're going to use try. We're going to try to execute these commands, and if there's a failure, we will then go to the exception, and we'll just simply print read fail. That's all we're really concerned with, read fail. If you want to dive into that more, I would recommend that you just take away the error handling and let the error occur, and then you get the cryptic message, and you can dig into it that way. Here we're just passing on it and going back to read again. I have found that I'll get about one failed reading about every a couple of hundred or 100 or so during my experimentation with it. And of course, that is at this faster speed. Remember, we should be going longer than a second. But here's what's happening. We're going to read the sensor. We're going to store it in a variable called TC for temperature in Celsius. We're going to read it. H will be a reading from the sensor. We're going to get the humidity value. Temperature Celsius, we're going to add in that offset to get it online with how you calibrated it. That's that variable we assigned right here. So if it's always reading a 1 degree Celsius too low, you could add 1 up there. And when this line executes, it will create that offset and get it on target. Same thing for our humidity. We're going to add in our compensation or our offset value to get it on target. We're going to round that variable now because that'll be a float, and you don't want to deal with that. Our temperature in Fahrenheit, us Americans, we just got to stick with our Fahrenheit stuff. We need to convert our Celsius temperature by multiplying it times 1.8 and adding 32 to it. Then we'll round that floating point number down to something reasonable. Having 0.003 or 0.3 digits or decimal places of precision on temperature is a little ridiculous for a sensor that is plus or minus 2 degrees Celsius. So we're just getting it up to a whole number. Here we're going to convert those variables of TF, TC, and H into a string variable. And that way it's a little easier to print with, and we'll see another purpose for it a little bit later on. So really just read the data, offset it a little bit if it's out of calibration, convert it to another unit of measure, and then convert the variable or the data into a string format. And then finally, we're just going to print the temperature in Fahrenheit. This is America. We're going to do that first. Temperature in Celsius, noting it with the letter C, and then the humidity, and then the number of reads. So we'll go ahead and run this right now. And where I'm at right now, it's 69 degrees Fahrenheit, 20.7 in Celsius, and 35% humidity. And we've got our number of reads from 19 down to 0 for a total of 20 reads. Not so bad, right? Now, all around, this did take a little bit of working around to get it all to function right on my end for other purposes I'm going to have with the sensor. But right out of the box, you should be able to get yours up and going pretty quickly with this code. But after I got to this point, I thought, you know what? I think we should add some data logging to it. That would be much more useful for my application because there's certain rooms within my residence that I really need to monitor both temperature and humidity for health reasons. So I am going to then add in some code to data log this. And we'll put that into a file format that is easy to read and load into a spreadsheet for further analysis. I've already done a similar thing with other data in the past. I've got a video on that as well, so I'll explain that idea in more detail in that video, but for here, we'll still go over it in some brevity. Now, as I typically do, I had the font a little bit small, and I had the file section open in Thonny. So you may not have noticed that because I zoomed in on just the code portion of Thonny when in post-process editing. So here I've got our logger program loaded into Thonny, and I've zoomed up the font as big as I can make it. I'm really sorry, folks. I try like heck to keep that straight for you and make life good for you. But this is the program that I came up with for logging temperature and humidity. And this will be stored internally to the Pico rather than an external SD drive. The code, the base code in here is the same as it was in the previous example, so we're going to discuss the additional things that we've added. For example, the log file name, and this will be on the Pico. We're going to call it TH, temperature humidity -log. We're going to log data, and it's in a CVS file format, which we can import directly into a spreadsheet with the data pieces separated via commas. And we're going to be writing to it, and that's what the W denotes here. All this is the same, all this is the same, all this is the same. And then I added these 3 lines of code to actually write and log the data. We're going to create a variable called text, which will contain the temperature in Celsius with a comma, temperature in Fahrenheit with a comma, and then humidity, and we're going to add to that a new line character so that each new line is separate as it's imported into the spreadsheet. Then, using the command log file write, the text, that writes it to a buffer, so to speak, and then when we say log file.flush, that actually puts it into the file on the Pico. And in case you lost track of that, log file is the name of the log file, or the log file object, if you will, that we created up here. That's all there is to it. So what we'll do, we'll go ahead and run that right now. And for the most part, you won't see much different here. But what is different, I'm going to open up my files again. And now inside the Pico is a file called th-log.cvs. Okay, not so bad. Now, if you try to just open this from here, I think we get an alarm. So I'm going to try it. You'll get an error. So I found the simple way around that is to open Raspberry Pi Pico and open it up this way. And there's our data, 20.7, 69 Fahrenheit, and then 35% relative humidity. And of course, in such a short period of time, there was virtually no change in data. So now what we'll do is we'll take a look at how to import that into a spreadsheet. And I use LibreOffice, so that'll be my spreadsheet of choice to demonstrate this with. Before I can load into the spreadsheet, I need to get this file somewhere on the PC rather than inside the Pico. Now, on my desktop, I should have a temp. I will copy or download that to that temp folder. So that's my desktop. So now I will say open in LibreOffice. They call it Calc. We will go to desktop, temp, and it's going to ask us about importing that data. And as you can see down here, all its assumptions, our separator, we're separating by both comma, semicolon, and tab. Sees any one of those characters and it'll put it in separate fields as it shows here. Click OK. And there's your data. Hold on, folks. I'm going to help you out here. There's the data that you can see in your spreadsheet, and of course you can analyze it and graph it and do all kinds of wonderful things inside of a spreadsheet. So that kind of handles the data logging and all that fun stuff and data analysis via spreadsheet, quite simplistically with our little Pico. Now, there is something else that's missing, and that would be real-time consideration, so that we could also log what date and time the data was recorded. I got a solution for that, and I will add that to this project or this code a few months from now, or maybe even a month. It's kind of hard to say with how the schedule is going to work out. Where we will be using the Wi-Fi portion of this Pico. Perhaps you noticed that I did select a Pico W, and I did have plans to do something with this device as an IoT device, but I want to refine the code a little bit more, so that'll be an addition to this project in a future video. There's another thing I really wanted to add to this one, and just having this laying around in the house somewhere's not real cool, not attractive. I'm quite certain my wife would say, that's ugly, get rid of it. So I decided that I should design a little holder for all this so that it's just kind of interesting to the eye. This will be what the Pico will go in along with the sensors. So now we'll go about and take this crazy thing and make it a holder for our temperature and humidity sensor. Here are the three pieces for the stand. Assembly will be with cyanoacrylate glue, or commonly known as super glue. The sensor itself will go inside there, and I'll just use hot glue from a hot glue gun to hold that in place. That will go like so. Then we're going to fish this wire up through this tube. Notice it's a hollow tube. We'll fish the wire up through there. We'll get these pieces assembled. Then we will install the Pico in here, like so. And the wires would be coming out through here into there and connected onto the back side of this. And those will be just soldered in. This one's got the headers. I'll be using one without headers. And I'll just solder these leads directly onto the Pico as if they were the headers. If you don't yet have the ability to make up your own DuPont wires or connector systems like this, you can use your header connectors, DuPont header connectors with female ends on both ends. Another source would be for the RC industry, radio control industry, for servo motors. They have oftentimes extension cables, etc., that you can use as well. But you will have to watch the length. Once I get this all finished up here, I'll tell you what the length is that you'll need to make it easy on you. So that I understand what I've got at the other end of the wires, I'm using white on my signal or data line, V for my voltage, 3.3 volts in our case, and then black wire for ground. Now my next step is get this in here like so, and a few dabs of hot glue. Now with that glue pretty well set up, I don't have to worry about the sensor coming out. I can join these two components together. And I'm using cyanoacrylate glue. I found that the gap filling, medium viscosity, works out pretty good for PLA plastics that we 3D print with. So a few dabs of that, and we'll let that cure up. Now at this point, my wires are about 12 inches long from the sensor all the way through the tube and then hanging out the back. So if you're buying headers or jumper wires, etc., servo extension wires. Keep that in mind as a rough idea what you'll have to need for wires. Of course, the other option is too, you don't need to have the header connection, the DuPont connector at this end. You can always just solder directly to the sensor as well. And with the wires folded back in a little loop like that, that can go in there like so. And I'm going to take a couple of very tiny, probably number 1 Phillips screws, and I'll put those in to hold the Pico into the base. Before I do that though, I'm going to put a small dab of super glue right in this area here, where the tube comes in, and glue that together so that they don't move around. So I'll be right back after that setup. So I'll be right back after that little task. The screws that I used were M1.4 by 5 millimeters long. It was a little tricky getting them in, but I was able to do it. But as you can see, the wires are all concealed underneath. This is the post, or the tube is securely attached to the base with the super glue. The head is attached to the tube with super glue, and your sensor is attached with the hot melt glue. You could also use hot melt glue to hold in your Pico as well. Works perfectly fine for a lot of electronic projects. But that's the unit. Not so bad looking. Looks a lot better than a couple of electronic components laying on a table somewhere. And now back to the code, and we're going to give it one last test drive to make sure all is good. Seems to be reading fine. Look at the files. Oh, won't let me do that, but we can open it this way, and there's my data. How cool is that? All right, so now I've got a relatively attractive looking temperature and humidity data logger. Of course, you can run that off a battery pack or a power bank like I do for my video clock here. You can get these. They will support running that for probably a day or two, a very small, simple one like this. Otherwise, you get a power adapter, plug it into the wall, and you can run it like that. You plug it in, and she'll start running. Of course, you do have to save the file as a main program. So we would, at this point in our code, make our last changes, such as right there. We're going to change that to a sleep of time that would be the equivalent of 15 minutes or 20 minutes, whatever suits your fancy. You would save it or change that to that, save it into the Pico as a main.py program, and now she'll run every time you plug her in and turn her on. Well, I think that is a fairly attractive looking temperature and humidity data logger. Hopefully you guys enjoy it too. Of course, there will be files on my website for the code, the fritzing diagram, the data sheet, and the STL files for the design so you can 3D print your own stand. So that's going to wrap it up for this project for now. Remember, I will be coming back to this, and we'll be adding Wi-Fi functionality to it for IoT or whatever the buzzword of the day is. And so be sure to look forward to that one. I'm going to guess somewhere between a month and 2 months from right now when you see it. So that'll wrap it up. Thanks again for watching. I certainly hope if you enjoyed this or found value of the information I presented here, that you'll both like, share, and subscribe. I greatly appreciate it, and it would certainly help with the survival of this video or YouTube channel. Thanks again. Look forward to seeing you next time.